Welcome back, everybody. Welcome to the second session of the day today. And so the first speaker is Laurence Kotlikoff on a paper with a couple of courses on making carbon taxation a generational win-win. So Larry, the floor is yours.
Great. Thanks very much to the organizers for inviting us. We're my co-authors and I are delighted to participate in this, I think, very interesting and timely conference. So this is the list of co-authors. I want to make special mention of Andrey Polbin, who's in large part the brains and the brawn, and certainly, well, he's the brains and the brawn for this paper. He's at the Russian Presidential Academy of National Economy and Public Administration, also the Gaidar Institute in Moscow. So this is a truly international coalition of authors. Our focus is on studying carbon taxation as an externality. Over the years, it hasn't been studied that often, at least in large-scale models in that manner. It's been considered as a social planner problem. And we're concerned that that's taking the wrong approach from an economics perspective, because when you have a negative externality, there's a potential for a Pareto improvement, and that means there's a potential for a win-win. So we have a model here of the global economy as a single model of the world, and we're looking for the potential to make every generation uniformly better off on a compensating differential basis in terms of a percentage increase in consumption relative to what they would have enjoyed in the business as usual, no policy, equilibrium transition. Everybody, as you'll see in our preferred calibration, is going to get about a 5% welfare gain. So we're coming up with a calculation to produce a generational win-win. The okay, let's see. Need to get this thing to. Oh yeah, here we go. Okay, so climate change is arguably, well, maybe it's clearly the planet's worst externality. It could be reducing GDP by 1/3 within 200 years. It portends massive human suffering. We know that from the first presentation this morning that if we have the sea level rise that we're told about, we could have a huge fraction of, well, Bangladesh would be probably just underwater, but large parts of the U.S. Coastal areas would be underwater as well, including all the major cities. And then we have the concern about tipping points that was discussed as well. Now, how should economists address global climate change? We don't think the social planning approach is the correct way to do it. Social planners aren't interested in Pareto improvements. They care about one thing. They care just about their own welfare. And they're going to correct externalities that don't exist if they, for example, if they just care about people in the future and we didn't actually have any kind of a climate change problem, any carbon problem, a social planner would show up on Earth and put on a tax on carbon in order to improve the welfare of future generations, just because of that person's that social planner's preferences. So social planners kind of invoking a religion into economics here, and I can bring in summon my social planner from the heavens, and Alexander can summon his. We can all have our own different social planners, and they will all come up with different answers for what is the optimal carbon tax policy. And so what we're doing here is we're pitting future generations against current generations. that's not what economics says. And just to make clear that that's actually the case, I just want to read you a couple of sentences from Greta Thunberg's address to the United Nations 2 years ago. She said, "You are failing us," at the end of her talk, "but the young people are starting to understand your betrayal. The eyes of all future generations are upon you. And if you choose to fail us, I say, we will never forgive you." So we have definitely a generational conflict set up in the entire way we've been discussing this problem and the solution to it. We haven't, as economists pointed out, that there's a way to make everybody better off. So it doesn't have to be current generations versus future generations versus young and future generations. It can be a win-win. That's what economics tells us. And now the other approach to addressing this that is kind of similar to the social planner approach is to invoke an infinitely lived agent. Now, having such an agent with infinite, altruistic preferences that extend across that agent's descendants, that's computationally convenient, but it's empirically implausible. We just don't see any evidence of the kind of altruism that would be required to produce that kind of a effective utility function. We don't have evidence supporting Robert Barro's model of intergenerational altruism. On the contrary, we have evidence that's very strong against such altruism. Tests in the US, at least, for sure, strongly reject intergenerational altruism. And if we had such altruism going on, this carbon problem would already be resolved, because all these different dynasties, even if they were not altruistically linked, which they would become via intermarriage, so we'd have one big happy dynasty. But even if you had dynasties that were not intermarrying through time, we would have all these dynasties agreeing that they need to fix this problem, and they would elect leaders in the world to impose carbon taxes on them. And so the existence of this problem that we're facing is kind of proof positive that we do not have the intergenerational altruism that underlies the infinitely lived agent model. So how should we address climate change as economists? By modeling this problem for what it is. It's not a social welfare problem, it's an externality, negative externality, and it's caused by selfish life cycle agents. So we need to have a model of selfish life cycle agents, not a model of people that are altruistic towards their kids, and because that's not really what the world we live in. So we should be looking for Pareto improvements, efficiency gains, and then we should be thinking about how can we distribute those gains across generations. And I'm not talking just about current generations, but future generations as well. And our focus in this paper is on a uniform welfare gain to everybody currently alive and coming in the future, because we think that's the politically most likely to get adopted. If everybody can see that they have an equal stake in terms of percentage gain in a given solution, that can potentially be adopted. So imagine that Greta had said in her speech at the UN that you folks are, all you older people that I'm addressing are complete jerks. We know you're immoral. We know you don't care about us. Fine, let's cut a deal. Let's cut a deal by we're going to ask you to put on a carbon tax, but we're going to ask you to do something else that's going to help you. So yes, your energy prices are going to go up, but we're going to ask you to also cut other taxes. If you like, run deficits, that's one way this could be implemented. There's a zillion different ways we can describe this implementation, but cut your taxes so that you're actually on balance better off, let's say by 4.69%. and leave us the bill, leave us a bigger debt, official debt to pay, and we'll pay the interest, we'll service the debt through time. And we'll be better off because on balance, the gain to us from your reducing your emissions will offset the additional tax that we're going to have to pay. So this is the mechanism by which we can make everybody better off. We just use fiscal policy. And in our model, we're implementing this kind of a policy implicitly through lump sum redistribution across generations. And by the way, we have a paper underway that is a regional version of this, and we're finding similar optimal carbon tax and growth of the carbon tax through time. And there are some regions that, we have 17 regions in this additional new work that we'll be coming out with shortly. And some of the regions are benefiting from climate change and others are being hurt. And the ones that are benefiting, we need to compensate people in those regions for the fact that they won't benefit from climate change. And so what we show in this new paper is coming is that you can make everybody across the planet better off to the same uniform degree by the same percentage. And we actually compute that. Anyway, let me just tell you the model that we construct. So we have an OLG model. They live, the agents live from 20 to 75. The model assumes the Nordhaus dice carbon, temperature, and damage functions. We assume there's 3 dirty energies, coal, oil, and gas, and that each is being extracted at increasing costs. There's no uncertainty in this model. We do have another paper that's we've produced about the need for taxing carbon just because of the risk of climate change, not even because of the average cost or expected cost. In that model, we've set the expected cost to 0 and show that just the risk alone is a good argument for wanting to tax carbon. And indeed, the carbon tax for that reason could be larger than what would be needed just if you had a deterministic setting. So we're assuming in our model that there's a clean energy sector and that we have a fixed factor, you can think of it as land, that limits the production in the short run of clean energy. But through time, clean energy's productivity is growing at a faster rate than overall productivity. So over time, what you have is clean energy eventually taking over and dirty energy ending up not being used. But in the business as usual, the no policy scenario, this happens after about 125 years, whereas you'll see that with the optimal carbon tax, the end date for dirty energy is advanced, happens much sooner, about 50 years earlier. So there's no uncertainty, no tipping points in this model. We do in the paper consider different climate damage levels. So we're taking the Nordhaus function and damage function and taking the quadratic term and increasing it by a factor of either 1x, so that's the Nordhaus function, 3x or 6x. I'm going to focus on the 6x case, which is going to produce damages in the no policy scenario that are after year 2 into the next century, totaling about 29%, 30% of world GDP, and about 20% of world GDP at the end of this century. So our carbon tax policy is an initial tax, and there's also a growth rate in that tax. We also have consider in the paper having 2 different growth rates, a short-term growth rate and longer-term growth rate. There's not any discernible difference in terms of the optimum solution. So we think that what we're using for tax instruments here really spans pretty much the optimal instrument set. And then we're capturing essentially all the efficiency gains. And we're using this lump sum redistribution to achieve this uniform welfare gain. And that lump sum redistribution authority has to break even in present value. So we put on the carbon tax, we lump sum rebate those carbon tax revenues to the energy companies. So we're keeping the revenues kind of out of the picture. Then in addition to that, we have this lump sum redistribution across generations that breaks even in present value. So the government is not generating any net revenue. It's not changing its consumption. We're just, it's living within its intertemporal budget with the policy. Okay, what are the main findings? Well, carbon taxation can dramatically reduce damages in our model. If we're talking about, I'm just going to flip to what we think are the more realistic damages, the 6X case. The optimal tax there is $70 a ton of carbon, and it rises annually at 1.5%. The uniform welfare gain is almost 5%, as I mentioned. You have to subsidize early generations by as much as 10% of their consumption. It's like giving them 10% more consumption in the general equilibrium here. So I just want to emphasize that the equilibrium solution and the one we're simulating, we don't do the transfers and net taxes and transfers, lump sum redistribution after the fact. It's all part of the equilibrium solution. So some early generations get compensated as much as 10% of their consumption, and future generations, depending on what, they can be taxed by as much as half of their consumption. But nonetheless, all generations are ending up with, on balance, a 4.969% welfare gain. And we also simulate in our model, in our paper, the infinite lived agent case, which is just taking these OLG preferences and extending them into the future. And we do that in order to do like a apples to apples comparison between the OLG model and the infinitely lived agent model. And the first thing to say is that the optimal solution for the infinitely lived agent model doesn't achieve a Pareto improvement. So the social planner, the infinite lived agent solution, where you have these dynasties that are free riding on each other, and then we find the optimum for them. And again, we don't think they would free ride, because they would all have an incentive to elect governments that would impose carbon taxes. But that aside, we are following some of the literature here that is focused on this model, and assuming that there is no coordination by these different infinitely lived dynasties. And the point then is that since these dynasties can redistribute within their own within their own means to different members, they don't have any interest necessarily in, well, let me put it this way. If we solve that problem, and the model really was one in which the world really was one in which we had selfish life cycle agents, then the ILA policy, the infinitely lived agent policy, that doesn't have the lump sum redistribution would not achieve a Pareto improvement. Some people get hurt relative to others. And the two policy solutions can be very different, as I'll show you, and they're very different in terms of the level and growth rate of the tax rates of the tax. In addition, the OLG policy is less sensitive to time preference. So that's with the Stern report and other people weighed in about exactly what the optimal time preference for the social planner to have should be. Well, we think that's like a religious debate and not an economic discussion, and that it's time to end the religious discussion and get back to the economics. So obviously there's lots of literature I could discuss here, but I don't have time. But these are the giants who contributed, and a number of these people listed here at the bottom in particular have focused on OLG models and made the same point that we're making. We're just doing it in a larger scale version of the model, of the life cycle model. So we're not the first ones to realize that we should be modeling this as a negative externality where you can achieve Pareto improvements. Okay, so here's our model. We've got output being produced with capital, labor, and energy. Cobb-Douglas energy depends on clean energy S, oil, gas, and coal, and these coefficients put everything into the same equivalent units. And then the clean energy is produced with land and capital and labor. And the nice thing about this land, again, is that it really is proxying for the fact that certain, that the world doesn't have an infinite supply of hydroelectric capacity or of wind or land that could be used to where you can erect turbines and get green energy that way. So there's limitations, and that's what the H is capturing, but the B coefficient here is moving rapidly through time faster than the A coefficient, growing. And then the other thing that's nice about this formulation is that in the short run, when B is not that big, because H is fixed, it's always the optimal to have some green energy being produced. And that's an important thing. We wouldn't want a model where there's no green energy being produced until some date and then it flips on. We want to have in effect, a smooth transition. So these are just the first order conditions about hiring factors of production. P here is the price of energy, and delta is the depreciation rate, N is the rental rate on land. The extraction costs are given by this complicated equation, which we estimate these coefficients. These are the reserves. So if we're talking about, let's say, M being G for gas, then we have coefficients that are we have a nonlinear function which involves the reduction in reserves of gas. And so M is standing for coal, oil, or gas. And each energy company is trying to maximize its value. And that's, this is the new production M of the particular dirty energy. And this is the price that it's the dirty of energy. And these are the extraction costs. And this is picking up the tax on carbon. And then this capital TAL is the rebate of the revenues that are being collected. That's a lump sum rebate. So it doesn't enter into the first order conditions. So firms do face this tax in deciding whether to produce output with more capital labor and less energy. They basically substitute away from energy. And when they produce less energy, that means they're going to produce less emissions. So, we have some, just to go back here a second, some conditions on reserves can't be negative. And those are captured by Kuhn-Tucker conditions in the first order conditions. I don't need to take you through those. Okay, so we have on the household side, the demand side, we've got households with a kind of a CARA utility function and a budget constraint, and their assets have to equal their supply of assets have to, in total across all the generations equal, well, the demand for assets has to equal the supply, which is government debt, and which is being, is a way of describing this lump sum redistribution authority as having a debt, and Q's the value of land, and then we've got the value of the oil company, the dirty energy companies, and we've got capital. So, and government debt is evolving in this manner, and we've got factor market equilibrium conditions. So, in the infinitely lived agent model, is the same utility function, except we have a single budget constraint that's not generation specific. It's basically the dynasty's assets next period equal its assets this period plus its saving, nothing particularly different. That's just the standard story. This is the DICE formulation for damages which affect TFP. Z is the growth rate of TFP that would happen without any carbon damages. The D's the carbon damages. This is the atmospheric temperature. You see it's not quadratic. We're taking the DICE parameter theta2 and multiplying it by a factor of 6 in the case I'm going to focus on. And then we have how, a formulation for how carbon in the atmosphere in the upper and lower oceans is evolving. And those, the atmospheric carbon concentration is producing a forcing variable F, which impacts then the temperature increase. So this is all quite standard to people in this, we're familiar with this literature. This is a discussion of the steady state. I'm going to jump over that. We have in this model global population change that the UN is forecasting. So we have new generations coming along that are larger in size to capture the demographics that are being projected in the economy. And now I just want to show you the damages in our base case with no 6X case with business as usual, no policy. You can see that in year 200, we've got about a 30% of GDP, of global GDP being lost due to climate change. And even after year 100, we have about a 23% reduction. With our optimal policy, this is reduced down to 8%. So rather than a 23% loss, we've got an 8% loss. This is the uniform welfare improving damage level. And in the long run, and well, in year 200, it's about, it's reduced by, well, not by more than by 8% from, it's 8% damages rather than 29%. So it's a pretty substantial reduction. So carbon taxation matters in our model. And here's the case we're focused on. These parameters, time preference rate of 1.5%, a long-run growth rate in the price of energy that's declining by 0.5%. And the optimal solution is, as I mentioned, a $70 carbon tax with a 1.5% growth rate. And if you have a somewhat higher or lower or higher time preference rate, there's some difference in the initial tax, but the growth rate is the same. So it's not hugely sensitive to the time preference rate. And then this table showing you that these lump sum transfers for a generation born in the year 200, it's 50% of their lifetime consumption in the 6X damage case. And they have to pay a negative, they get a negative transfer. In other words, they have to pay a tax. But people in the long run are not being taxed as heavily. And in the short run, there are transfers to early generations. So that's what Greta is saying. Look, we're going to give you early generations on balance some money to make you better off by 5%, just like we're going to be better off by 5%. Let's cut a deal. Let's do the deal. Now, we could give all the gains, well, efficiency gains to the generations already around. In that case, their gain would be more like 9%. And if we gave it all to future generations, it would also be a little bit higher 9.2%. The optimal taxes would not be that much different. Let me say on the issue of the green paradox, if we delayed the optimal, if we said we can't do anything for 20 years in terms of any carbon tax, we have to wait till then. Well, then the efficiency gains that are possible, the uniform welfare gain drops roughly in half. So waiting matters. Delay is not a good thing, because you delay, you run into the green paradox, you start to incentivize the dirty energy companies to use it or lose it, and you lose roughly half of the potential efficiency gains just by doing nothing for too long. And the, okay, I'm going to skip over that. I want to just show you a comparison of the optimal tax in the 6X damage case under the infinite lived agent case versus the OLG case. You can see that the optimal carbon tax, $70 in our model. With the ILA case, it's $90. Our tax is growing at 1.5%. That's the optimal solution. In the ILA model, it's growing at 3%. So over time, the differences in these tax policies is enormous. And this chart also this table also shows you that the optimal tax, not the growth rate, but the optimal initial tax under the ILA is much more sensitive to the time preference factor rho than is the optimal initial tax under the life cycle OLG model. Okay, the interest rates in the long run are quite different. If you have this OLG model in which you're in effect redistributing to young and early generations, some of which are young already right now, but also older current generations, there's going to be crowding out of capital, and that's going to lead to higher long-term interest rates than would arise in the ILA solution, where the long-run marginal product of capital is being pegged by the time preference factor. That guy. Let me just show you a picture here of what the optimal policy looks like. This is again for the 6X damage case. This is coal production. Business as usual is this light blue dotted line. So you can see that after about 120 years, we have clean energy taking over completely. But there's been a lot of damage done by that point. But the optimal tax policy involves shutting down coal immediately. With oil, the optimal tax policy involves pretty much the same oil production and also the same gas production for quite a while, but then there's a divergence. But oil and gas production end around year 70. So we're going from like 120 to year 70. That's like 50 years sooner that we end the use of dirty energy completely. And we have some other pictures here that show you, for example, the damages are quite substantial with business as usual, but they're much reduced with the optimal policy. Let's see if there's anything else I want to show you. That's pretty much it. I'm about a minute under time, so I'll stop here and take any response.
Good, thank you. Let me take questions from the floor.
Larry, can I ask a question? Larry, this is an incredibly basic question, but I want to make sure I understand. Where are the resources to make the transfer to the current generation coming from? Is that from investment? i.e., are we the way you make the transfer to the current generation is by increasing the consumption share of GDP and reducing the investment share of GDP? Is that how the transfer takes place?
That's exactly how it works in real terms. Yeah. Yep. We just leave future generations with less capital because, I mean, it's not, there's no bequest in this model. It's just that they, every generation's shows up and they have accumulated less capital because they had to pay early generations got to consume more, and then younger people had to pay, and so they couldn't save as much in the form of capital, and so they bring less capital into the next period, and so that process, just like pay as you go, Social Security crowding out the capital stock, no different.
So instead of the LSRAs, you could in principle also do the redistribution of consumption taxes, right?
Could we redistribute this with consumption taxation?
Yes.
Yeah, except that there would be impacts of that on the intertemporal allocation of consumption for every generation. So you'd be introducing distortions with respect to that choice. So that wouldn't necessarily be, that would kind of confuse matters. We're trying to say, look, let's just kind of focus on the gains, the efficiency gains from carbon taxation, not muddy the waters. But you're right, Alex, that we don't have lump sum taxes and transfers. So it would be useful to explore more realistic redistribution mechanisms. That's
you can think about the lump sum elements as changes in the general progressive tax code, which you do not model because you don't have redistribution within generations. But for me, it's always harder to think about negative lump sum transfers that you will have in the future. That's why I'm asking this question.
Yeah, that's true. But if you have nonlinear progressive taxes, a lot of that is inframarginal taxation too. So for the high earners, who are going to be paying most of the taxes anyway. So I'm not sure that I think lump sum taxes have a kind of a bad rap, that there's more lump sum taxes out there available than most people think.
Okay.
But I mean, for people that are kind of not familiar with OLG models, because this individual infinitely lived agent model has really taken over macro and public finance for decades now. And so this all seems like a mystery, how to get this whole thing to work, to give everybody a uniform worker game. But, the technology for doing this, we had papers on this, Alan Auerbach and I, back in 1980, 81. So it's been around a long time, how to do this. And
there's one question in the chat I would like to pass on and rephrase it a little bit. So what's the intuition for the fact that the size of the discount factor matters less for optimal carbon taxation in case of the OLG? And a related question is, could you design a discount function in the Euler model so that you get the OLG back result?
well, so the first question is about, if you lower or raise the time preference rate in the ILA model, you're putting more or less weight on future generations relative to current generations. So when that in the OLG model, when you change the time preference rate, it just changes your weight on consuming today versus later in life, but it doesn't have any implications for trying to make future generations better off. It's not saying that somehow we think future generations should get more or less weight in what is effectively a social welfare function. And then the other question is, so basically, just to say it a different way, you're invoking a God with these preferences because we don't have intergenerational altruistic people. So you're kind of, it's like a shorthand for a social planner. That's really what's going on here. And you're deciding how much you love future generations versus current generations, how much your God does, or how much you're referring to a social planner, but you as an economist are actually saying, my preferences about ethics here are very important. Everybody should pay attention to my preferences over anybody else's preferences, because I know what the true ethical thing to do is. But we can't do that in economics. You can move to philosophy and do that, but you can't do that in economics. And then the second question is, could we take a social planner and manipulate their preferences to get to this uniform welfare improving gain? And we've heard that from a number of people, because they're so stuck on the social planner framework that they somehow want to rescue it and make it. My guess is that you could, with enough, you should be able to probably do that, but I'm not sure, because that model is different. The model has a whole different long run steady state. It's the marginal product of capital is pegged by the time preference factor. You'd have to introduce capital income taxes to try and, so it's not just a simple matter of adjusting the time preference rate. You have to probably do it through time. You have to be time specific. It seems to me to be kind of a thought exercise that misses the point. The point is, we don't have that kind of, that's not the right preference structure to start with. Right one is selfish generations who don't give a damn, just as Greta said, about anybody else except themselves. And that's what we see. But let's deal with that fact and make everybody uniformly better off. Or, that's what we bring to the table as economists, not. So I think, unfortunately, this whole literature, I think, got off on the wrong foot and took the profession down the wrong path and has generated a generational war over this issue, and kind of convinced everybody. If you look in our country, the Republicans, I think as a party, think it's a zero sum. It's either us or them in the future. And what are they going to do for us, right? Well, they have a lot they can do for us. 5% welfare gain is a significant number. So I think if we'd been discussing this way from the beginning, we would probably have some consensus, and also understand that we can do this across regions as well. Have the US, for example, subsidize Russia, because that's the way it needs to go for Russia to agree, because they're giving up something. Anyway, I think Thomas might have a question.
Yeah, Larry, I'm interested into the damage function. I guess it's no secret by now that I think it's a real challenge to estimate these. But I don't know the DICE model well enough to really understand what you have done here. Is it that you increase the social cost of 1 ton CO2 emissions from roughly $30 in the DICE model like some years ago to $180? Or could you say a bit more about what you really did with the damage function and how this works in the DICE model?
So the DICE model again has this damage function that affects total factor productivity, and he's got Nordhaus has these coefficients, and we just took the quadratic coefficient and increased by a factor of 6 in order to have our model under the no policy scenario produce a 30% of GDP, world GDP output loss in the year 200. So that's kind of how we calibrated that number 6. Now, we're not in this new work. We're dealing with a regional model, and that the model that's regional. We're moving to the Crucell-Smith damage function, which is shows that there can be negative damages, gains for countries that have very cold to begin with and become warmer, like Canada or Russia. So we're not wedded to any particular damage function. Our thrust here is, I think the story is still out as to how big the damage function, what the right damage function is. That's the point that Bob's been making for a long time now. None of us really know for sure, but our major contribution, we think, here is just to frame the question in a more appropriate manner. And again, we're not the first ones to do but we're the first ones to do it in a large scale framework.
Just one short note, maybe I heavily question that even countries like Russia or Canada will benefit, from climate change. I mean, that's a long debate, for what reasons, but there will be very few winners in this.
I hear you, and we're going to do a lot of sensitivity analysis around that, around those regional damage functions.
Good, thank you. Thanks everybody. So then let's stop here, I suggest, and move on to the next speaker, which is Bob Pindyck on climate and other catastrophes.
I'm going to tell a very different story from the one you just heard. Here's the plan. Let me go through these, go through the outline. What I want to do is, first of all, just very briefly go over some things that we know and don't know about climate change. And there's a lot we don't know. That's why this story is going to look very different from what Larry told you. He told you what's going to happen, and I'm going to tell you that we don't know at all what's going to happen, therefore we don't know the social cost of carbon. I'm going to argue that what matters really is the chance of a catastrophic outcome. A catastrophic outcome could be the kind of thing that Larry mentioned, a 30% drop in GDP or something like that. And the reason for that is if you consider sort of middle of the road outcomes, whether based on IPCC projections or whatever, you just don't get much in the way of a social cost of carbon, and hard to justify doing much now. So the real question is, how likely is a catastrophic outcome? What kind of impact might it have? And how do you assess this? How do you think about the likelihood of a climate catastrophe? I've said this before, I don't want to dwell on it, but these models are useless for this. Maybe expert elicitation is the way to go. I've done some work on that, and I'll show you a few results. There's another issue, and that is that once we're in the world of catastrophes, well, why stop with climate? There are other potential catastrophes. In fact, one's already happened. It's called COVID, the pandemic, but there's a bunch of others. So, I've done work showing that these things are not independent, and basing policy on just one can be misleading. So that's the plan. Here's what we know and what we don't know. What we know that as we burn carbon, the atmospheric CO2 concentration is increasing. It will eventually, there's a delay, but it will eventually cause warming, possibly higher sea levels, stronger hurricanes, and more. And that these changes, climate changes, are on net bad. They'll reduce GDP broadly defined. We have to include things like the extinction of species and health effects and all of that. It'll reduce GDP broadly defined, and it will hurt social welfare. And that means that there's a social cost of carbon. There's an externality, and the full cost of burning a ton of carbon is greater than the private cost. And that social cost of carbon is important because it's the basis of a carbon tax or equivalent policy. Here's what we don't know. How large is the social cost of carbon? So the estimates range from $15 a ton to well over $200 a ton. That's today. And then it could rise in the future, but that's today. Huge range of estimates. Why can't we use models, these integrated assessment models, use the DICE model, or, there's so many of them. The answer is they are extremely limited in what they can tell us. The damage function is one aspect of that. I'll show you some others. They just don't give us information. Again, what matters? The chance of a catastrophic outcome, and we have to think about how we can look at that. The models. The basic approach is to project future emissions of CO2 under business as usual, and then one or more abatement scenarios. There's some uncertainty, but this is plausible. That's okay. Given future emissions or projected emissions, project the atmospheric CO2 concentration over the next 100 or 200 years. There's some uncertainty here because that concentration, this is not a linear function, but it's plausible. I mean, we can do something that's plausible here. Now we know we have a projection of the CO2 concentration. What is the temperature increase that's going to result? And that's called climate sensitivity. Climate sensitivity is defined as the percentage increase, the increase in temperature in degrees Celsius that will result in equilibrium from a doubling of the atmospheric CO2 concentration. In equilibrium is complicated. That could take many, many years, but usually what we do is we look at this and say, within 30, 40, 50 years, we're most of the way there. So let's use the following definition for climate sensitivity. If we double the CO2 concentration, how much will the global mean temperature go up after 30, 40 years or so? All right, we don't know. The uncertainty is huge. There have been many, many studies by climate scientists of climate sensitivity, and we have distributions. We have probability distributions for the IPCC. The most likely, that's the 66% confidence interval, most likely range is 1.5 to 4.5. That's a factor of 3. That's just most likely. If you include what's possible, the possible range goes from 1 to 6. The number that's usually used and that appears in the DICE model and most models is 3, and 3 is in the middle of the range of 1.5 to 4.5. But we don't know climate sensitivity is 3. We know that it's a positive number, but it could be anywhere. It could be 1.5, it could be 4.5. Here's a nice model. Those of you who like simple models, here's my model. If climate sensitivity turns out to be 1 or 1.5, if that's what we learn, forget about climate change. Nothing's going to happen. If climate sensitivity turns out to be 4.5 or 5, we are all toast. So you better go to your lawyer and rewrite your will because we're done. The fact is, we don't know what it is. All right, but let's suppose we could come up with a number for climate sensitivity. Then what? Now we know what happens to temperature. What does that do to GDP? We don't have a clue. Nothing. No theory, no empirics, nada, nothing. We don't know anything about what that's going to do to GDP. So lastly, I mean, if we ignore that little problem and we simply project losses of GDP, then we need a discount rate. And that's another big issue. I mean, what's the right discount rate? Economists don't agree on this. There are a lot of problems with the discount rate, the role of uncertainty, and so on. And the result of all this is you can get any number you want for the social cost of carbon. One of my colleagues, I won't mention his name right now, told me, you know, I can make a model tie my shoelaces. And that's right. You can make the model give you any number you want. And there's a problem here. And this is really why I, tend to go off like this on these models. I think models are very useful and I build them myself. They're extremely useful to help us get an understanding of things, how things relate to each other and things that might matter or not matter. But when they're used to make projections, it creates a misleading perception of knowledge and precision that's just not there. So it's this misleading sense of scientific knowledge that's what I find the problem with these models. All right, the damage function. So here is what this is. It just says it's a loss function, L of T. T is the global mean temperature. If the global mean, and it's the change in the global mean temperature, the increase in temperature is T. If the increase is 0, then L of 0 is 1. The bigger is T, the lower is L, and GDP is L of T times GDP with no warming, GDP star. And here's what Larry showed us. This is the Nordhaus DICE model. It's an inverse quadratic, all right? And you got to remember, this is a totally arbitrary function. Comes out of nowhere. It's made up to show how GDP goes down when T goes up. It's not based on any theory, any physical theory, economic theory, any theory. It's not based on any data. It's just made up. Now, that means you can multiply by 3, you can multiply by 6, you can multiply by whatever you want, because it's all made up anyway. Okay, we don't know what would happen to GDP if the temperature increases by 3 degrees Celsius or whatever. And by the way, in the original DICE model, these parameters, alpha and beta, were chosen so that if you have a 2 degrees of warming, you know, you'd have what Nordhaus wrote as common wisdom regarding the loss, maybe a 2% loss. But who knows if that common wisdom is correct? We don't have any experience with these kinds of temperature increases. We don't have data, and that's a real problem. The difficulty here is that what we do know or think is that the warming that occurs is going to occur slowly. Larry's model ran over, I think, 200 years. I hope we'll have another conference in 200 years to see where we are. But anyway, you know, 200 years is a long, long time. 50 years is a long, long time. And over those long periods when warming slowly happens, there's adaptation. How much adaptation will occur? We don't know. We think there'll be adaptation, but very hard to know how much. Really, it comes down to guesswork. Let me just show you a couple of examples of adaptation for those of you who are skeptical about this. We've had adaptation. We've had climate change. Here's the climate change. Those of you in Europe might know that, you know, when the settlers came to the United States, they landed on the East Coast. That's where the colonies were, okay? And so the population was on the East Coast, and gradually people moved west. And when they moved west, there was climate change. I don't mean over time. I mean the climate in Indiana, in Missouri, in Iowa was very different from the climate in Pennsylvania and New York, New Jersey, and so on. All right, that's what I mean by climate change. So in the 1850s, most wheat was produced where the people lived, which is the East Coast. Not the coast, but in New York State, Pennsylvania, in the East. That's where most wheat was produced. People were moving west and had settled in the West. And when they went out west, they dug holes in the ground and said, this is amazing. You know, if you dig holes in the ground in Massachusetts, you get rocks. If you dig holes in the ground in Kansas, in Iowa, it's rich soil, rich, dark soil. And they said, this is amazing. Let's plant wheat here. And they did, but it didn't grow. And the reason was climate change or climate difference. The problem was that in the Midwest, it was hotter in the summer and colder in the winter. And the wheat that had been grown in the East simply couldn't flourish in the Midwest. So what happened? Well, what happened is called hybrid corn, hybrid wheat. We developed new strains of wheat and corn and other grains that would grow in the Midwest. And today, that's where most of our grains are grown. We don't grow stuff like this very much in Pennsylvania or New York. We grow them in the Midwest because we now have hybrid strains of wheat and corn. That's called adaptation. Here's another example. Hurricane Sandy flooded southern Manhattan. Well, there's a plan to build a seawall around Manhattan. It's just a plan. Whether it'll ever happen, who knows? If it does happen, well, that's a form of adaptation. If the sea levels rise, does it mean that New York is going to be totally flooded? Maybe, maybe not. If we build a seawall, it won't be. Remember, the Netherlands is below sea, much of the Netherlands is below sea level, and yet people live there. Why? Because of dikes, because there's protection from the sea. Okay, that's adaptation. Other examples, you know, technical change that happens very slowly, more efficient heating and cooling, flood resistant construction technologies, better seawalls and flood walls. I think the Dutch began building seawalls about 800 years ago, the earliest dikes. The dikes today are very different from the ones 100 years ago or even 50, 60 years ago. Hybrid grains, more efficient irrigation, geoengineering is a form of adaptation. Regulatory change. Right now we subsidize building in flood-prone areas. You want to build a house where it's going to get washed out to the sea? Don't worry about it. The federal government in the US will cover your losses. So we shouldn't do that. I mean, that's another way to adapt to rising sea levels. Is adaptation going to eliminate the problem? Probably not, but it makes predicting the impact of higher temperatures very difficult. Catastrophic outcomes. If the discount rate you use is 2% or greater, the most likely scenarios are going to imply a very small social cost of carbon. The US Interagency Working Group got a social cost of carbon of about $40. That was based on a 3% discount rate and an average of 3 integrated assessment models. That's a very small number. That's like a gasoline tax in the US of about 40 cents a gallon. Very, very small. By the way, why 3%? How did they arrive at 3%? Did they decide that that's the correct discount rate? No. Some people wanted 1 or 2%. Some people said 5%. After all, 5% was a market-based rate. You know why they picked 3%? Because they wanted to go home, and that was in the middle. Time to go home and be done with this. So that's where the 3% comes from. We don't have any consensus on what the right discount rate is. But again, the Interagency Working Group's estimate was based on most likely scenarios. And you know, if we knew that what's going to happen is what we're calling most likely, we could feel happy. You know, don't worry, be happy. But what if the outcome is not most likely? What if it's catastrophic? And what is catastrophic? Well, that's the kind of stuff that Larry was talking about, you know, 30% drop in GDP, 20%, 40%. That to me would be catastrophic, okay? And then if you consider a reasonable probability of that happening, you can get a much higher social cost of carbon. Oops. The models can tell us nothing about catastrophic outcomes, nothing, because we don't know what the climate sensitivity number is. We don't know the damage function. They tell us nothing about this. What are we going to do? How are we going to figure this out? So this is important. How do we estimate the social cost of carbon and evaluate the possibility of a catastrophe? One approach is to use rough subjective estimates. It's maybe the best we can do. You know, many years ago, this is what was done at the Defense Department, the RAND Corporation did these studies, looking at what was then the world's greatest catastrophic risk. I actually think it still could be. And that's the possibility of nuclear war. Back then, a US-Soviet nuclear exchange. How likely? What would happen? There was no data. There were no models. So analyses at that time were based on what was plausible. What would pass the following econometrics test, the laughability test, the plausibility test. That's how they looked at this. And maybe that's how we have to look at climate change, catastrophes. What is plausible? What's a range of catastrophic outcomes that we think, and probabilities for those outcomes, that we think would be acceptable to a broad range of economists and climate scientists? To me, that may be the most fruitful way to go about this. Because again, there's no models that we can build that are going to give us this answer. Given some plausible outcomes, where I define plausibility in terms of a range of economists and climate scientists agree that it's plausible, given those plausible outcomes and probabilities, we can calculate present values of benefits of averting outcomes or reducing the probabilities of their occurrence, okay? The other approach related to this is simple expert elicitation. And I did this recently. I surveyed economists and climate scientists, experts based on their publication records. And the objective analysis was the economic impact of climate change measured by reduction in GDP. And I ignored the mechanisms by which CO2 emissions cause climate change and how climate change can reduce GDP. All I cared about was, if we don't do anything, what would happen? And if we want to prevent that from happening, what would it take? By how much would we have to reduce emissions? Very simple. I looked only at outcomes in this expert elicitation. I wanted the probabilities of those outcomes. And again, what reduction in emissions growth is needed to avert an extreme outcome, to truncate the impact distribution. And with that information, I computed what I call an average social cost of carbon. Remember, the social cost of carbon is defined as a marginal thing. It's the way we do it in economics. The externalities are marginal. If you emit 1 extra ton of carbon, what does that do? What's the damage from that? Okay, that's a marginal measure. I looked at an average measure, which is the total benefit from truncating the impact distribution divided by the total emission reduction needed to truncate the impact distribution. So that's what I was looking for. And I did this for a whole bunch, many experts around the world. I looked at this for them individually and for groups, like all economists, all climate scientists, and so on. And this was published a couple of years ago, so you can look at this. I just want to show you a couple of graphs because it's interesting, I think. Here's economists versus climate scientists. These are individuals. So these histograms show the average SCC, average social cost of carbon estimates for individuals. And one thing you see is that economists have much lower numbers than climate scientists. Economists are much more skewed over to the left, numbers below, at or below $100 a ton. Whereas climate scientists, huge range and a much higher mean, $300 a ton versus 173 for economists. North America and Europe, I actually thought Europe would be higher, but it wasn't. They're almost identical. Here are all individuals, putting all the climate scientists and the Europeans and the American, everybody together. And this is the mean of this is just under $300 a ton. Well, what's interesting is there's huge dispersion. I mean, these numbers are all over. They're just huge dispersion. Now, you can look at this. Here's one more way to look at it. This is what's going to be what is the probability, the cumulative distribution function for the reduction in GDP? Again, huge dispersion. So, we have very high numbers. The averages are much higher than numbers used in US policy analysis. We get numbers well above $200 a ton, but huge dispersion. What does it mean? There's so much disagreement that maybe this means that there's so much disagreement that we can't rely on expert opinion. I mean, if the experts are all over the place, how can we rely on them? What use is it? On the other hand, we might say that we're using too broad a set of experts. And it turned out when I trimmed the sample, what I did, one of the questions I asked is, what's your degree of confidence? How confident are you? And if I got rid of all the answers where the confidence was low, I got lower numbers for the SCC. So is the right number, $200-300 a ton, $80 a ton? It's hard to say because it depends on what your view is of expertise. Either way, this is a lot higher than the numbers that are being used now, at least in the United States. A lot of uncertainty. One very important point, because I've written about this and talked about all the uncertainty, I've been accused of being a climate denier, and I'm not. And I want to emphasize, I mean, I've said this in my papers, people don't read it, that I've said this numerous times. The fact that there's uncertainty doesn't mean you shouldn't do anything. What it means is, in fact, you may want to do a lot because we need insurance. A carbon tax is a form of an insurance policy. The problem is, how big should that tax be? And there's one more complication. I said we have to focus on catastrophes, catastrophic outcomes. But once we're in the world of catastrophes, shouldn't we look at other catastrophes? Shouldn't we worry about pandemics? And, I've been doing this work with Ian Martin from LSE, and when we wrote this, there had been no COVID, but we looked at what the CDC had been saying way before COVID, and the CDC said, it's coming, just wait, it's coming. It's going to be big and bad and more frequent, and it's coming. So we said that's a potential catastrophe, pandemics, bad pandemics. And by the way, the CDC says today, more are coming, not just strains of COVID, but new ones are going to come. And what about nuclear terrorism? Graham Allison at the Kennedy School says 50% probability that there'll be a major nuclear terrorist event, meaning blowing up a big city, in the next 10 years. Maybe he's too pessimistic, I don't know. But that's certainly an issue. Bioterrorism, extreme earthquakes, you go on, you have your own list of things you dream about at night. Can we treat these one by one and get a benefit cost ratio for each one? And the answer is no, they are interdependent. And the reason they're interdependent is because they're not incremental. So conventional cost benefit analysis breaks down. And this is the basis of work Ian Martin and I have done. It's in our 2015 paper. We have a new paper that just came out in the Economic Journal that deals with this and focuses on pandemics as well. All right, quickly, the conclusions here. There's a lot we don't know about. And to me, it's very important to be clear about what we don't know about and not make believe that we do know about things that we don't know about. I know that people like to hear, this is what's going to happen. In 30 years, sea levels are going to rise by X meters, as opposed to, well, sea levels might rise, they might not rise, they might rise this much, that much. People want numbers, but the fact is we don't know, and we should be honest about it. Don't make believe we know more than we really do. And what matters here for policy is the possibility of a catastrophic outcome. This is tough. We don't have data. We don't have theory. We have very little to work with. We can look at experts. We can look at what's plausible. We can't do a whole lot beyond that. And given the uncertainty, the focus has to be on insurance value. Focus on the extent of the uncertainty. What does that mean for the insurance value of early action? All right, let me stop here. I think I'm a couple of minutes early. What is it? Yeah, 2 minutes early. So let me stop here and take your questions, comments, whatever.
Thank you very much. So let me take questions from the floor. So one question in the chat is a little bit related to mine, and also like to the integrated assessment models. Would you say that if you don't take them as predictions or projections, but to evaluate alternative policies under the same functional form assumptions, and then make statements like the one policy is more effective by that amount of increasing social welfare than the other policy is? So that would tone down the use of the models and would still allow one to make quantitative statements.
So here's the problem, and I understand that. What you want to do is you want to compare policy A to policy B. Policy A is a big carbon tax, and policy B is a small carbon tax, let's say, all right? And you want to say, what's the impact of those two policies? And so what we're going to do is we're going to take the damage function. It's an inverse quadratic in the DICE model, and we're going to use it just to compare those policies, see which one is better. And we do it, and we find out that policy, I already forgot which is which, but we find out that policy A is better than policy B. Now let's change the damage function. Instead of an inverse quadratic, let's make it an inverse cubic. I mean, there's no theory. There's no reason why not. Okay, or do what Larry did, multiply by 6. Okay, now we get the opposite result. Now policy B is better than policy A. You see the problem? If we don't know the damage function, we don't know the damage function. It's tough, but that's life.
So suppose I want to do what you suggest, focus on the insurance value. How would my actions change if I follow your recommendation here? Or what should I do?
I'm assuming you want to come up with policy. You want to come up with a climate policy. So again, what you should do is ask, look, what might happen? What bad thing might happen? Larry said that I think Larry said, well, with certainty, we're going to have a 30% drop in GDP. I mean, I don't think that's certain. I don't think we can be certain of that, but whatever. Think about possible bad things that'll happen. Focus on the really bad outcomes. The normal outcomes, the middle of the road outcomes are irrelevant. They don't matter. They're not going to affect anything. So look at what is the chance, what are possibilities for a very bad outcome, And how do we come up with those possibilities? You're going to have to ask people who've studied this and ask what's plausible. Ask the climate scientists, what do you think? How likely is a 5-degree increase in temperature? And what might that do? There's a lot of work out there now on what 5 degrees might do to, or might not do to sea levels, to the strength of hurricanes. And there's work out there. There's a lot of uncertainty, but at least there's some work about what might happen to sea levels and what that might do to coastlines and so on. And then think about what could we do to adapt and what could we do to prevent this from happening? What kind of tax could we use? And by the way, coming up with a tax is difficult because let's say we had a $100 a ton tax. What would that do? By how much would we reduce carbon emissions with a $100 tax? We don't know. We don't know what the elasticities are of carbon use, carbon burning, vis-a-vis the price of carbon. We have rough estimates, but there's a lot of uncertainty there too. But that's how I would do it. And in the end, it's going to be what kind of insurance do I want to buy? And I also think that what's needed is another kind of insurance, adaptation. We have to work on things like, and this is, the environmentalists hate this word. They go crazy when they hear it. Geoengineering. Yeah, I said it. And I hope I didn't see how many participants hung up. Not too many. So we need to do research on solar geoengineering because we may decide that, look, we need to reduce emissions, get emissions to zero. That's what we got to do. Reduce emissions to zero by 2050. Well, what happens if we don't succeed? We have to be realistic about what we can do. It's not just what we should do. What are we going to do? Are we really going to reduce emissions to zero by 2050? The UK is supposed to. Are they really going to? What happens if they don't? Who goes to jail if they don't? Will China? So we need to think about what might happen, not just what we'd like to happen. And then buy insurance. Solar geoengineering technologies are simply a form of insurance. Maybe we won't need it, but we want to have it in case we do.
Thanks. So let me take it there. A couple of questions. So earlier I interrupted Thomas, and so let's take him first, and then we have Larry, Rick, and Solomon who raised their hands, and let me take that in this order. So
yeah, thanks, Alex. Thanks for the interesting talk. I mean, I fully agree that focusing on average model results is garbage. Yeah, we have to consider the risk of the extreme outcomes, and I now also wonder if really what we really need is a debate about which risks are acceptable and which risks are simply not acceptable at all. And then society should do whatever it takes to avoid these risks. And this might not sound realistic if the economic cost, at least in the shorter term, is high. But don't we just right now all witness that if it gets really bad, politicians or our society basically sacrifices the economy? I mean, we have it now with COVID at when the health system gets to capacity, nearly every country on the planet goes into lockdown, whatever it takes. So maybe focusing on these absolute limits, what's acceptable, independent of the economy, is a very important component here of how our societies work. And most climate scientists would definitely think that in terms of human suffering, climate change is at least comparable to COVID, but it's further away and it's not so immediate. So maybe it's a bit heretic because I'm talking to economists here, and I got the impression right now I see how society actually acts without much care about economy, which is very surprising to me sometimes. So the economy is still important, but I mean, should we think differently? Because we right now see actually that apparently something else is driving societal and political decisions. It's not the economy anymore. Or maybe I'm on the wrong track and the economy is still like the big fish, and yeah.
Well, just two things. First of all, when I did this expert elicitation, the survey, about half the people I surveyed were climate scientists, not just economists. They tended to be more pessimistic about what would happen, what could happen. And their average social cost of carbon was almost twice as high, but there was still huge dispersion. And many climate scientists were at the left end of the tail, that they didn't think, this was a huge, huge problem. Some were. Again, a huge amount of dispersion. As far as COVID is concerned, COVID happened all of a sudden, and there was no simple adaptation to COVID. I mean, the adaptation was go home and what we're doing now, go home and stay home. That was the adaptation. There was no, we can do the following things to reduce the impact. So COVID had a huge impact on the economy, the world economy, and it's very different from what we anticipate with climate change.
Just one more comment on this. What I'm trying to say is maybe for the societal decision, the GDP impact is really not the crucial thing. If we as a global society decide it's not acceptable that some countries will go underwater, we basically eradicate them, then we might do things to avoid this independent of the economy, because small island countries going underwater will not have a big impact on global GDP at all, but it might still be unacceptable.
Right. No, that's certainly a possibility. And we worry about big countries being flooded, Bangladesh, Thailand, although there's already a lot of land underwater, under sea level in those places. But you're right, there are island countries which conceivably could be eradicated, go underwater. We may decide that's unacceptable. That's possible. I don't know how much broad agreement there'd be about that, but that's certainly one way to look at it.
I think one of the things that is interesting that we're seeing now is a focus on a date for net zero for economies as a whole, for companies. In a sense, that is the cost benefit outcome. And it says these societies are more or less feeling like whatever the costs are and the benefits are, this is a reasonable outcome. And so it focuses on quantity rather than price. And it seems to me if we were to adopt that point of view, we can let the cost of carbon, valid carbon offsets and mitigation and even trading carbon certificates to lead us toward that kind of a goal without actually having to determine what the social cost of carbon is.
Right, Rob, I agree with you. And I think it's natural that's where we ended up, because there is no agreement. We're not going to get an agreement on the social cost of carbon. So what's happened instead is we come up with targets. We start out with a temperature target. So the temperature target was 2 degrees. We can't let the temperature go above that. Maybe that's too high. Maybe it should be 1.5 degrees. Even if it's 2 degrees, what is it going to take? Well, maybe if the world goes to net zero emissions by 2050, maybe that would do it. Maybe not. And so then we end up with a target that's a little easier for everybody to kind of focus on, and let's try to meet that target. I think that's fine. I think the problem is that it's extremely unlikely that the world is going to get to net zero by 2050. I think it's unlikely that Europe and the US, is the UK part of Europe? I guess I should say Europe, the UK, and the US will get to net zero by 2050. But for the world as a whole, my own view is I can't imagine that happening. But maybe I'm too pessimistic. I work a lot on catastrophes now, so I'm a pessimist. But I understand why the focus moves from a social cost of carbon, figuring out the tax, to a target for emissions. Just one thing about that, and I raised this in a lecture I gave at LSE recently. Look, there's another argument the other way, and the argument the other way is that a harmonized carbon tax is in some way it's easier to get an international agreement, because the problem with the net zero, you're not going to get India to agree to net zero by 2050, and I doubt China would agree, or Indonesia, and the long list. And so how much does each country have to reduce its emissions? And then how do you know they're abiding by what they said they do? And what do you do if they don't abide by it? The nice thing about a harmonized carbon tax, it's just one number that we agree on. And each country collects its own tax, and the government uses it any way they want. And that's nice because governments like to collect tax revenue. In this way, they can collect tax revenue and they say, the devil made me do it. I didn't want to tax, your gasoline and all that. It's horrible, but they made me do it. But now they have money that they can spend. So that's the argument the other way in favor of a carbon tax.
Yeah.
Can we move on, and let me suggest that I take the questions of Larry, or we take the questions of Larry, Rick, and Solomon, and you ask the questions, and then can you answer to all of these questions in one? So just
can I answer all 3 questions with one answer?
Yeah, something like that, exactly.
Why not?
Okay. So
Maybe
let's
I
try.
can answer before they ask the questions. Go ahead.
So Bob, I think the focus on the social cost of carbon and the distribution of religious beliefs by different people is kind of not particularly interesting or economic, to tell you the truth. I'm not sure we can learn anything from that calculation, because I don't think the social cost of carbon is independent of some underlying time preference ethical evaluation. But the efficiency gain from dealing with these problems is independent of that, at least theoretically. Now, in terms of practically calculating what an optimal carbon tax is, in the paper I just presented, we took basically like a certainty equivalent kind of formulation by saying, let's look at a parameterization that produces 30% of GDP loss, which seems to be at the upper end of what people think is the worst case scenario. And you find, when you look at the paper, that the optimal carbon tax is not much different in terms of the, even if you use like not a $70 initial tax, but a $30 initial tax, because the damages were really 1x rather than 6x, you'd still get essentially the same efficiency gains in the 6x case that you'd have in if you use a $70 tax rather than a $30 tax to begin with. So writing down these models in a more systematic way helps you find out whether whether a range of damages is leading to pretty much the same carbon policy for a range of damages, or whether their damage function is particularly sensitive, or some combination of the damage function and the impact of carbon on temperature. So I think, and then the last thing I want to say really quickly is that, so we have this paper about carbon risk taxation, and you're talking about risk. So we should formally model, we do in this paper, Pareto gains, where the gains are with respect to expected utility, not with respect to certain utility, but expected utility. We still don't have to deal with anything involving social cost of carbon, which to me is undefined, but we can certainly incorporate informal ways. They're not back of the envelope calculations. All these concerns you have about the probability of sea level rising this much or that much. I just think we're at the beginning stages of modeling this, but I feel like you're sending off like a nihilistic vibe here. Let's kind of forget economics and just kind of do some forget more formal modeling, forget large scale modeling, because it's too arbitrary. I think it's not that arbitrary. And I think it's a start, the more detailed the model, the better, but we need to do it in a sensible model, the selfishness of generations, and get back to economics on that.
And if it's fine, let's move on with Rick.
Okay. So that was a very good presentation. I enjoyed it very much. So when I speak to climate scientists and people like that, they say that these temperature caps or emissions cap are to avoid the risks of tipping points. So of real big disasters. So I think that seems to me a pretty good reason to take those temperature caps seriously. And if you then speak to Madame Lagarde, the European Central Bank, or the Network for Greening the Financial Systems, or national governments, they're all in this mode of caps, and they're not in a mode of SEC. So they all want caps. But here's my problem. So with these caps, then these integrated assessment models start doing these cap calculations, and then they find very fast growth rates. So not like an interest rate of 3 or 4%, but maybe 7 or 8%, in England even 15% per year. So that means they're postponing all the action into the future and not doing very much upfront, and doing all the action in the future, like every politician. So then the rate of interest, the rate at which the carbon prices have to grow becomes a political thing again. Whereas with the social cost of carbon, most of these models, they grow roughly at the rate of growth of the economy, like maybe 2% per year. And then at least you get more upfront. So I think it's for all kinds of reasons, the temperature cap is easier to explain to politicians, it's easier to work with, but there are some issues to do with not enough front loading of carbon pricing.
Thanks. Then Solomon, please.
Hi, Bob. Thanks for the presentation. I guess my question is quite simple. I've always been a little fascinated by your argument that we know very little and yet we should rely on expert elicitation. So I guess I'm just curious where you believe experts are getting their information from.
Good, thank you.
I'll try to answer all these. First, I think with Rick, it's easy. Yes, you're right. I understand the focus on caps, and you're right. I mean, there's this question of front loading or future loading. It's easy to push things off. Let me go backwards and Solomon's question of where do the experts get their information? I don't know where they get their information. It could be from models. It could be from studies they've done. I think a lot of the climate scientists get their information. They've worked on parts of this. A lot of climate scientists have worked on pieces of this whole thing, like sea level changes. That's a whole area within climate science. And they may get this from models they've worked on. They may get this from studies they've done, from what they've learned from other people. They tend not to use integrated assessment models. That's the economists like those things. Economists like these integrated assessment models because there's an economy, an economic model, it's kind of all the way we build models. And I think that in the end, what matters is, what do people think? This is all we can do. What's plausible? And again, I would go to not what's going to happen, but what's plausible. And then, let me turn back to Larry, where Larry says, look, if there's an efficiency loss of 30%, we don't know if there's going to be a 30% loss of GDP. I mean, maybe there will. That'd be quite something. We don't know. We just don't know. And, you may say that I'm kind of nihilistic and I'm telling us to forget large scale modeling. This is going to show my age, and Larry, your age, and others here who share our age. But think back to the 70s, the models in macro. See, I see Rob is grinning, that we used to build. The MIT the MIT FRB model, and the Wharton model, and Otto Eckstein's model, all these big macro models we used to build. And they were incredibly complex, hundreds of equations that were used to predict what would inflation be, what was the interest rate going to be, and so on. We don't do that anymore. I mean, we stopped doing that a long time ago because we don't think that's a useful way to spend time. And I think that's kind of what's going to happen here. Larry, you're suggesting that we do more detailed models and, be careful about the details. I actually don't think that's going to help us because we don't know what to put in those models. Just like how many years ago, 50, 45 years ago, whatever it is, we didn't know what the right way was to model investment behavior and how investment behavior depends on GDP, anticipated GDP growth, and so on and so forth. We didn't know the relationships, and we didn't have the econometric tools weren't very useful at that time. So I don't think making these models more detailed is really going to help us. Maybe I'm nihilistic, pessimistic, I don't know, but that's where I am.